Okay, so for the axial force worked example, we're told that we're to use a particular column section. So I'll come on to what these mean in a second, but basically we have the height, the width, and then for column sections or H sections, we have the weight in kilograms per metre, so per metre run of the section. And we're told that we're to find both the material yield load and the critical buckling load about the major and the minor bending axes for a 3 metre tall steel column with pin-pinned boundary conditions. So again, we'll come on just to explain what we mean by them in a second. And I've also just given a little bit of extra information, so we can assume that we've got grade 355 steel. So that means that we can take a yield stress of 355 newtons per millimetre squared, or 355 megapascals. And I've also given the information that we can assume a Young's modulus for steel of 205 gigapascals. And the other parts of the question, so part B is simply to state the maximum axial force the column can resist. So this is obviously going to take into account all of the values that were calculated in part A. And then finally part C is really just to check that our simplified rectangular calculations will return very similar values for the cross-sectional area, the second moment of area about the x1 axis, and also the second moment of area about the x2 axis. And I'm just noting that for convenience, values in the section tables are generally given for area in centimetres squared, and then for the second moments of area in centimetres to the 4. But it's much more usual for us to use official SI units. So for area, we're going to use millimetres squared, and then for second moments of area, we're going to use millimetres to the 4. So a UK column section, sometimes referred to as an H section, looks like this. So the first dimension that we were given, 152, is the height approximately in millimetres. The second dimension, the breadth, is obviously the width approximately in millimetres again. And then, as I mentioned before, the final figure that we're given to identify the cross section is the weight in kilograms per metre. So when you look up the section tables, these are the first three figures that will appear in the section tables, and obviously you can then read the other values that we're interested in just by running across the line in the section tables. One thing to mention is some section tables run across 2 pages, so you just need to be aware of that and make sure you're extracting the information for the appropriate section. Okay, so for part A, what I've done is I've just written down, and I generally do this for any question that I'm answering, I've written down the information we have, so I've written down the cross-section, I've written down the Young's modulus, and I've written down the yield stress value. And then I've just gone across in the section tables and noting, obviously again, that the section tables are in centimetres squared for area, I've multiplied that through by 10 squared to get us the value in millimetres squared. And for the second moments of area, I11 and I22, I've multiplied through by 10 to the 4 to take us from centimetres to the 4 to millimetres to the 4. So the next thing I've done is I've obviously then just drawn out the boundary conditions that we have, so you can see that here. So I've noted down that we're dealing with a 3 metre column. We've got pinned boundary conditions, and that means that when we look at the Euler buckling load, the constant that we're going to put in is simply 1, because the boundary conditions aren't going to change the effective length when this buckles at all. So just before I go on to calculate the Euler buckling loads about the major and the minor bending axis, it's just worth clarifying which 2 axes they are for a column section. So the major bending axis is this one running across here. So in the way we're setting everything up, this is our x1 axis, so it's the axis that we're calculating the second moment of area I11 about. And then the minor bending axis, so the minor bending axis is the axis that is easiest to bend the column about, is this axis here, x2. So it's obviously the axis that we're calculating the second moment of area I22 about. So, going on to calculate the different loads which either material yield will occur or at which Euler buckling will occur. So for the material yield load, we simply multiply the yield stress by the area A here, and so that gives us approximately 1300 kilonewtons as the material yield load. For the Euler buckling load, what I've done is I've done one calculation using I11. So in this case, I11 is the same as Imax. So this is about the major bending axis. And then I've done one calculation using Imin. And in this case, this will be the same as I22. So this is obviously about the minor bending axis. And so for buckling about the major bending axis, we get a value of about 3900 kilonewtons, so clearly well in excess of the material yield load. But for the minor bending axis, we get a buckling or a Euler buckling load of around 12 to 1300 kilonewtons. And so we can see that for this case, this is just below the material yield load. So obviously this is actually the critical axial load, at which point our elastic design would begin to fail. So in part B, I'm just obviously confirming what we've just gone through in part A. So I'm confirming that the maximum axial force that the column can be expected to resist is the lowest force that we calculated when we were looking at buckling about the major and the minor bending axes, and also when we were looking at the material yield load. So it's the one that we found for the Euler buckling load when we have buckling about the minor bending axis. Moving on to part C, what I've done is I've taken all of the dimensions from the section tables, and then I've worked out a few additional dimensions. So in particular, I've worked out this centerline dimension here, and I've also worked out effectively the depth of the web alone here. So to calculate the area, I've obviously already divided the section up effectively into three rectangles. So we can see the first part here. This is simply the area from the two flanges, and then the second part here is the area from the web. And we end up with this value, which is very close to the one in the section tables, and will only be different because obviously we're missing out these small radial components that would actually be present in the H section here, here, and here. In order to calculate the second moments of area, we're just using the parallel axis formulation. So you can see here, this is for the two flanges. So obviously, when we're calculating the second moment of area about the x1 axis, the value that gets cubed is simply the thickness for the flanges, and then this part here is for the web part. We then go on, so we have the two areas of the flanges, so this is just the area being calculated here, and then obviously times the x2 bar squared component. So what I've done here is I've taken my centerline distance, and obviously I simply divide by 2 to go effectively from the centroid, which will be here height-wise, up or down to the respective flanges. We don't need to include any additional component for the web, because obviously the centre of the area for the web is the same position as the centroid for the entire cross-section, and so we've included all of the terms we need, and we simply end up with this value here. Again, if we check that compared to the value in the section tables, it's very close, it's slightly conservative, again because we haven't included the material present in the radial parts at these four locations. So finally, for the I22 value, so the second moment of area about the x2 axis, and obviously the x2 axis is running vertically here, we have the local contributions from the flanges and also the local contribution from the web here. And because the centres of areas of all of the areas, so the two flanges and the web, are all actually coincident on the x2 axis, so basically their x1 bar value is equal to 0. We don't actually have any additional contributions for this term, and so we calculate the value of I22 here. And again, if we check back, this is ever so slightly lower than the value reported in the section tables.